Okay, the next topics are those related to the exercise, which is generally supposed to be a sort of resume, a sort of summary of all the argument of analysis one, at least up to now, except perhaps integrals, but sometimes also with integrals, which is the study of functions. So what does one mean by the study of function? So the purpose is, is to draw the qualitative graph of a given function. So this means that you have to collect information in this qualitative graph, and the information to be collected is information to be collected is the domain so the behavior of the boundary of the domain in particular asymptotic behavior. And so the intervals of monotonicity. So the intervals of the domain in which the function is monotonically increasing or decreasing. So these are the intervals of monotonicity. And this includes the study of the maxima and minima. In both senses, local and global. And the intervals of convexity. This is the only word, the only notion that we have to introduce. So here we have intervals of convexity. And in particular, the study of the inflection points. Okay? So, all of these points are well known except the last one, and we know what are intervals of monotonicity, the intervals in which the function is monotone, either decreasing or increasing, but we don't know how to find these intervals, and the answer is surprisingly simple and is related to the derivative, in particular to the sign of the derivative. So the subsection here is the relationship between derivative and monotonicity. So the theorem is the following. You have a function f differentiable in AB. Then first, If the derivative of f in the interval AB is non-negative, then f is monotonically increasing in AB. And on the other hand, here, this can be inversed. If f is monotonically increasing in AB and f is differentiable in AB, then the derivative is not non-negative. Second, if the derivative is strictly positive, so f prime of x larger than 0 for every x in AB, then f is strictly monotonically increasing in AB. So, and this is the proof. And first, let the 2 points x and y be in the interval AB with x less than y. Then by Lagrange theorem, applied to the function f in the interval xy, implies that there exists a c in xy, which is included in AB, such that f of y minus f of x is equal to f prime of c times y minus x. Okay, now, since c is in AB, the derivative, we are in the first point of the theorem, so the derivative is non-negative, so larger than or equal to 0, while y minus x is larger than 0, so this quantity is not smaller than 0. That implies that f of y is not smaller than f of x. Then, by definition of monotonically increasing function, f is monotonically increasing in AB. And now let us see, still for point 1, but the inverse. The inverse direction says that let x bar in AB x in AB and x larger than x bar, then the incremental ratio we consider the incremental ratio f of x minus f of x bar divided by x minus x bar. So f of x minus f of x bar is, sorry here, not smaller than 0, and here x minus x bar is larger than 0, then by the permanence of sign, when we compute the limit for x going to x bar, since f is differentiable at x bar, this converges to f prime of x bar. Then by permanence of sign, this f prime of x bar must be not smaller than 0. This is by permanence of sign. And now we go to the second part of the theorem. Here the hypothesis is just that f prime of x is larger than 0, strictly larger than 0. So exactly as in point 1, so and first arrow here, we have that f of y minus f of x is equal to f prime of c times y minus x. This time f prime of c is positive, y minus x is positive, so their product is positive too. And then we can conclude that f is strictly monotonically increasing. And so we will mainly use this part of the theorem, the second part of the theorem, in our study of function. So let me give you a remark. The remark says that the last arrow, here the arrow I pointed to cannot be inversed. This is wrong. So the remark says that f, so I can copy it from here, so f strictly monotonically increasing in AB does not imply that f prime of x is strictly larger than 0 for every x in AB. So be extremely careful in applying this theorem, because you cannot inverse it. At least you cannot inverse point 2. And so we have to show that something is false, so it is just a counterexample that is sufficient to show that. So the example, probably you already guess what is the simplest example available to show that. So we have f, domain is R, target set is R such that f of x is equal to x cubed. So f prime of x is equal to 3x squared equal to 0 for x equal to 0. However, if we consider x less than y, then x cubed, so f of x, is strictly less than y cubed. So f is strictly monotonically increasing. So in the graph is this. And so there are three possibilities. So if x and y are both positive, or x and y are both negative and x less than y, then in the interval xy, the derivative of f is strictly positive. Then, for the previous theorem, point 2, we have x cubed less than y cubed. So the only case missing now, the only case we have to cover is the following. If x is negative and y is positive, then also x cubed is negative and y cubed is positive. So f of x less than f of y. As a conclusion, f is strictly monotonically increasing on the whole real line. Okay? So you can easily prove this generalization of this example. So let me be more precise here. It's strictly monotonically increasing even though the derivative is not positive in all points of R. F prime of 0 is indeed equal to 0. And this is the very important thing to be underlined here. And now we generalize with this more or less straightforward generalization. So we have a function f from AB to R that is differentiable in AB, and f prime larger than 0 in all AB minus a finite set of points x1, xk. Then f is monotonically strictly increasing. It can be a good exercise for you at this point of the course to try to prove it. It is not difficult at all. You just have to isolate your study to every interval, and I write you the first line. Suppose x1 less than x2 less than xk. And this and then homework. So of course analogous result hold for monotonically decreasing functions. So in particular, if you have f, so for instance, not for instance, but namely, i.e., namely, f differentiable in AB and f prime of x non-positive for every x in AB implies and is implied by that fact that f is monotonically decreasing. Here f prime of x less than 0 for every x in AB implies that f is monotonically strictly decreasing. And so I want to show you in a very simple example how this works by proposing you the study of a very simple function. You probably know how to study this function without thinking of it, but I will go very slowly. I will be, as usual, extremely pedantic and horrible, as you know. So, the function is x times e to the minus x. So, study the function in the sense, draw a qualitative graph of f. So first, first you have to find the domain. You have to write the domain, and the domain is R. Second, the limits at the boundary of the domain. So the boundaries of the domain are minus infinity and plus infinity. So first, the limit for x going to minus infinity of x e to the minus x. So x goes to minus infinity. E to the minus x, when x goes to minus infinity, goes to plus infinity. So the product by minus infinity and plus infinity is in the algebra of limit of divergent function. This is equal to minus infinity. On the other hand, the limit for x going to plus infinity of x e to the minus x is equal to what? So here you already know, but I want to proceed very slowly. So x e to the minus x is equal to x divided by e to the x. Okay? And so it is a case infinity over infinity. So we want to proceed by the L'Hopital. So x prime e to the x prime. This is equal to 1 over e to the x. This ratio has a limit for x going to infinity, and this limit is 0 as x goes to plus infinity. So by the L'Hopital, we conclude that the limit for x going to plus infinity of x e to the minus x is equal to 0. Okay, so this function goes to minus infinity as x goes to minus infinity, and to 0 as x goes to 0. A second point, or a third point if you want, you can do it by second or by third, is the sign. So, of course, this is equal to the sign of x e to the minus x, which is equal to the sign of x times sign e to the minus x. The exponential is always positive, so this is equal to the sign of x. It does not change the sign. So the function is negative, so f of x is less than 0 for every x negative, and f of x is larger than 0 for every x positive. Okay. And now the next point are asymptotes. So here you have that limit. Since the limit for x going to plus infinity of f of x is equal to 0, this means that y equal to 0, so 0 is a constant. So y equal to 0, the x-axis is an horizontal right, because it is plus infinity, right, asymptote. And on the other hand, for going to minus infinity, here we have that x. So to have an asymptote, it can be slant or horizontal, but cannot be vertical at the minus infinity. To have an asymptote for x towards minus infinity, one must find two numbers p and q in R such that x e to the minus x is equal to mx plus q plus little o1. Namely, x e to the minus x minus mx minus q is infinitesimal as x goes to minus infinity. But you see that since here we have an exponential which is much faster than any line, any possible line, then this will dominate everything. But let us study it again slowly and pedantically. So here you gather x, and here you have e to the minus x minus m minus q. And of course, this product here, with this factor here in the product will go to minus infinity. To plus infinity. E to the minus x, when x goes to minus infinity, goes to plus infinity. While x goes to minus infinity. Minus q is a constant, doesn't go anywhere, it remains itself. So this is always something that goes to minus infinity for every m and q in R. Then there are no m, q such that x e to the minus x minus m times x minus q is little o1 as x goes to minus infinity. And then at the end we have monotonicity. This is the last point to be investigated. Monotonicity. And in order to discuss monotonicity, monotonicity intervals, let me write here also intervals. One has to study the derivative of x times e to the minus x. So f prime of x is equal to e to the minus x plus minus x e to the minus x. This is 1 minus x e to the minus x. It is very easy to be studied, and this is larger than 0 if x less than 1, smaller than 0 if x is larger than 1, and equal to 0 for x equal to 1. This is not 0, this is 1. It is always 1. Okay? So now we can draw we can draw a picture here. The qualitative study we wanted to obtain. So here you know that this goes to minus infinity. it will be very rough here. Passes through 0, then at 1 it arrives here, and then start decreasing up to 0. Very roughly. So this is the only graph, this is the only possible graph, by the aid of the soul. So this means information on the monotonicity only, and no information on convexity. Of course, there is some information more, because here at 1 we have differentiability, so here it is smooth. But what we cannot say here is whether the function is somewhat crying or somewhat smiling, and also here. But is the function crying or smiling? Concave or convex, which means concave means like that, crying, or like that, convex, smiling. This is an important question to be addressed, and we will study it. But before closing this video, I want to stress that just with this very rough, very elementary study, we can say that 1 is the global, x equal to 1 is the global maximum point, the unique global maximum point. In particular, it is local. And then there are no minimum points, neither local nor global. And this is all for now. And then, in order to pass to the study of the convexity and of the concavity, we have to pass through the study of critical points. And so let's go to the next video.